clustering. As we know, data is growing much faster than ever before, especially in areas like bioengineering, pattern recognition, social media, finance, and this list can go on and on. And big data can have high volume or high dimension, or both most of the time. So in my talk, you will see how why data reduction as a pre-processing step is critical to effective machine learning and data mining, and you will also see how to downsize the data without losing much information. Here is the outline. We will first talk about how to deal with high-dimensional data, or simply speaking, those wide tables with a large number of attributes. And there are essentially two ways: feature extraction and feature selection. Feature extraction transforms the existing features into a lower dimensional space, and feature selection, in contrast, selects the subset of features without any transformation. And the second topic in this talk will be talk about data clustering, which is a powerful tool for exploratory data analysis, which divides the population into a number of homogeneous groups. And data points in the same groups are more similar to each other rather than to other clusters. The process of describing the clustering is called profiling. And the segment profiling is an application of data clustering, which is helpful for customizing marketing strategy. And also creating predictive models separately on each segment may provide higher predictive power. First, why we need to reduce dimensionality. The first problem is computationally complexity. The many traditional statistical algorithms are MLE based, maximum likelihood based, and it starts with the calculation of covariance matrix, which can be computationally expensive when we have large number of features. And the second problem is interpretability. Or in other words, the insights between the inputs and the response. When we have large number of features, it's, the model complexity increases and so sacrifices the model interpretability. Third, noise accumulation in high-dimensional prediction has been recognized as a problem for a long time. And the paper published early in 2008, Jing Fan mentions that classification can be as bad as random guess when we have large number of features, which is close to or even bigger than the number of observations. Last but not least, multicollinearity is a notorious difficulty with high-dimensional data. And severe multicollinearity will increase the variance of the estimates and reduce the, make the estimates unstable. So after we understand all the problems, the need for dimension reduction becomes clear. And there are two main, as I mentioned, there are two main methods to reduce the dimensionality: feature extraction and feature selection. What does feature extraction do? Feature extraction techniques map the data, the original high-dimensional data, into new low-dimensional space, where important characteristics of the data are still preserved. And the new space gives a linear or nonlinear transformation of the original data. For example, principal component analysis, which I will talk about in, later. PCA gives a linear transformation. However, there are some nonlinear versions of PCA which project the data onto some kernel space. In the new space, we usually not just have a better visualization of the data, but also can understand, we also have the clustering and to have a good prediction. And we also have less redundancy so that we can improve the prediction. Like the principal components, those principal components are orthogonal to each other, so those as feature extracted are independent. And we also find that some projections in lower space can help reveal the distinct clusters that were not easy to detect in the original high-dimensional space. Some good examples of feature extractions are like principal component analysis, linear discriminant analysis, factor analysis, multi-dimensional scaling, and some nonlinear ones like isomap. However, feature extraction is not always good, and one major issue of it is the interpretability. Remember, we said like the original information got compressed in the new space, and any new features in the new space is a combination of several existing features. So it will be hard to explain how the original inputs affect the response eventually. So feature extraction is not always suitable if interpretability is critical in some industries. Principal component analysis, of course, is the most famous one among all those I mentioned. And PCA uses the dependency between variables to represent the data in a lower dimensional form without losing much information in terms of the variation in the data. And PCA has been widely used for dimension reduction, data visualization, pattern recognition, exploratory data analysis like clustering and etc. And it is an unsupervised method, which means it doesn't have labels or responses. So the data we use is a n by p matrix where each row is a p-dimensional feature vector. What we need is to summarize them by projecting down into a q-dimensional space where q is usually much smaller than p. Principal components are a sequence of orthogonal directions that maximizes the variance of the data projection. And if we use a simple toy data with only two variables, x1 and x2, suppose the data are linearly correlated on the diagonal line, then what do you think about this red line? Do you think it's a good representation of the data? The red line in the plot, do you think that represents the data? Yes, yeah. And so the red line across the data clouds most captures the variance in the data, and we know that the variation of the data is essentially the spread, and for this data, the spread is most on the diagonal line. So the red line is the first PC here, and it can be represented as a linear combination of x1, x2, multiplying the weights w and w2 respectively. But the question is, how can we calculate the weights w so that we maximize the data variance? And let's just keep that question for a minute. I will talk about that in the next several slides. And just say we already have the first PC determined, then the second PC is orthogonal to the first PC among all the and it maximizes the variance among all the orthogonal directions to the first PC. And again, the second PC can also be written as a linear combination of x1 and x2, but projecting onto a new vector v. So in this simple 2D case, the second PC is determined if given the first PC, and because there is only one orthogonal direction for the 2D case. And this is always the case for the last PC for any general Q-dimensional case. So this slide answers the question we had before, how to calculate the weight W. So in general, if we need to find the case PC, then we simply maximize the following optimization problem, which maximizes the variance in the projection under two constraints. The first is that the L2 norm of WK is 1, and also the case W is orthogonal to any previous W's. For estimation purpose, we replace the population covariance matrix with the sample covariance matrix, and using eigendecomposition, we can solve for all the W's. We know that covariance matrix is a symmetric, positive, semi-definite matrix, which can be decomposed as follows: S equal to A, D, A transpose, in which D is a diagonal matrix. That means only the diagonal entries are non-zero, and those are the eigenvalues of S. And the columns in A are the eigenvectors, all called PCs. We usually sort the eigenvalues to order the corresponding PCs. Here is an interesting example for using PCA doing facial recognition, and it's named eigenfaces. We use the ORL face database for demonstration, and the data set consists of 400 images of 40 people, 10 from each person. Those images are all taken at a upright position in frontal views, varying some lighting condition and facial expressions, but they are all taken against a dark homogeneous background. Each image here is a 64 by 64 pixel in the precision. So each feature vector, or we call a sample, corresponds to a 4096 by 1 vector. What we want to do is to classify the faces, so we would like to investigate the variance in face space. So the first step we need to do is to subtract the mean face. The mean face represents common elements that all faces have, and it can be simply calculated by taking the average of all the feature vectors. And the bottom plot shows how a mean face looks like. And the rest information in the images are essentially the variation in the facial features. So we use PCA to extract the information contained, or in other words, to capture the variation in a collection of faces. Then we will use the information extracted to encode and compare each individual. Eigenfaces are essentially the eigenvectors. We can plot eigenfaces as sort of ghostly face, because each original face contributes more or less to each eigenface. And by just looking at those eigenfaces pictures, we can tell that it not only encodes facial features, but also some illumination change in the image. And with those eigenfaces, we can reconstruct any image from its lower dimensional approximation, which is simply a linear combination of chosen number of eigenfaces multiplying their weights correspondingly, and of course we need to add a mean face back to get the actual look. For normal PCA, we usually use scree plot or proportional of variance explained to determine the proper number of PC, but in eigenfaces analysis, it's better to evaluate whether the reconstructed image has face-like, or most of the time it's also depend on what is your tolerance. Like in this example, the top 10 eigenvectors or eigenfaces are obviously not sufficient for a good reconstruction, and the top 50 may be sufficient to encode some important facial features, but if a really good reconstruction is required, then we need around 300 eigenfaces. And once we chose the best number of eigenfaces, we can use them or the corresponding weight as a new feature vector which represents the original image in the new eigenface space. So if any unlabeled face coming in, we can project it onto the new face, new space and recalculate the weights. In SAS via visualization data mining, visual data mining and machine learning, we can obtain eigenfaces and their weights easily by running ProcPCA. We first need to do is to do the stratified sampling by person ID to partition the data into train and test set as I described before. And here you can see like I specified the underbar part IND underbar equal to 1, which is the indicator that got generated from the partitioning step. And N here specified the number of eigenfaces chosen. And by default, ProcPCA centers and scales the data. Data centering essentially means subtracting the mean, but in this application, we do not need to do any scaling, so we specify the non-scale option. And the last statement here is the output statement, which outputs the principal component weights and those original variables after centering. As I mentioned, we usually use scriptplot to choose the number of PCs. And scriptplot displays the proportion of variance explained by each principal. Since since we order the PC on the x-axis, so this curve, this PVE curve, is always non-increasing, and it usually decays rapidly, which means that the majority of the variance in the data can be explained by the first several PCs. And to choose a number of components, we can either set a hard cutoff, say 80% of the total variance in the data, or look for the elbow shape, which this red arrow point to in the PVE curve. And there are also more sophisticated methods using cross-validation to choose the proper number of PC when we don't see such clear hockey shape in the plot. Feature extraction also reduces dimensionality. Instead of constructing new features in a lower dimensional space, it finds the best subset. The best subset contains the least number of features that most contribute to model accuracy or data variation. And the feature extraction techniques can be roughly grouped into two categories: supervised and unsupervised. Supervised selection algorithms identify attributes that are most relevant to target variable. And it can be done through some simple univariate analysis like chi-square or R-square test. Another kind of approach is to consider the selection as a search problem. For example, forward selection will start with no feature and add one feature each time. And backward selection, in contrast, start with all the features, then drop one, which is the least relevant to the target at each step. And the combination of forward and backward is called stepwise. The third group of algorithm, which is really important, is called embedded methods. And you probably heard about the term like regularization method, like lasso is the most common one in this group, in this category. And lasso introduces a regularization term called a penalty, which penalizes the model complexity. Unsupervised variable selection is generally difficult because it's hard to it's hard to determine the selection criteria directly. We have some methods that use the clustering results to see whether the attributes most contribute, see the features that contribute to the model based on the clustering results. So for example, if the clustering for a data set doesn't get changed by either feature A or feature B, then we think feature A, those two features are redundant. Or if a feature doesn't change the cluster discrimination, then we think this feature is irrelevant. There are also some solutions that try to eliminate the redundancy using similarity measures like correlation matrix or mutual information. And the var-reduced procedure, I will talk about it in the next slide, falls in this category. var-reduced performs both supervised and unsupervised feature selection. It identifies a set of variables that jointly explain the maximum variance of the maximum amount of data variance. And var-reduce uses forward selection, which means it starts with an empty set and add one variable at a time. Assume we want to select key features. X1 here denotes the set with selected features. And this red, the middle part in the following equations, which I highlighted here, represent the null space of X1. So for supervised learning, we have target variable Y, and by projecting Y onto the null space of X1, we can measure the variance that cannot be explained by X1. And so minimizing the first equation essentially means we're maximizing the variance in response that can be explained by selected features. Similarly, we can understand for this unsupervised learning. So X2 includes all the features that are not selected, and by projecting it onto the null space of X1, we can measure how much data variance that are not explained by X1. And so we minimize it. var-reduced procedure in SAS VIA allows you to specify which matrix the selection based on. Could be covariance, correlation, or squared sum of cross product. And there are also several stop criterion available, like maximum number of iterations, variance explained, or incremental variance explained. Under supervised learning, we can also specify some likelihood-based statistics like AIC or BIC as the stop criteria. And var-reduced procedure is quite useful. First of all, it's very efficient. It's fast and runs in parallel. And second, the unsupervised selection functionality of it can be really useful for some industry because we know that data labeling could be very expensive and very intense. And once we have the variable selected once we have the proc SG plot helps you to plot the BIC curve and see how the BIC statistics goes on with the number of iterations. In the next couple of slides, I will demonstrate a real project we did for analyzing marketing data, and the dimension reduction plays an important role in the final success of this project. The data was used for KDD Cup 2009 challenge, and the problem was to predict the propensity of customers either churn or switch service or upgrade their devices for a telecom company. And the data set consists of 15,000 features and 50,000 instances. And there are 206 out of 15,000 features are categorical ones. Although this data set has a moderate number of samples, but the number of features is quite large. And if we build a full model on all the features, then we know lots of them are irrelevant or redundant or noisy, so the model will suffer from the problems we mentioned before. The second problem in this analysis is imbalanced data, and there are fewer than 10% in the minority class. When we usually refer to imbalanced data in research papers, that means the minority class has like has a portion of 10 to 20%. But in this project, as well as in many real world cases, data can get far more imbalanced. For example, fraud detection detects frauds that happen less than 2% of all transactions. And many medical screening tests target on extremely tailed probabilities in the data distribution. And risk modeling using insurance data usually predict very rare events like car accident. And the conversion rate of online advertisement can go as low to 10 to -3 or 10 to -6. And there are many such examples in the real world. So as a data analyst, we will all encounter such problems under certain circumstances. Conventional methods are often biased towards the majority class because their goal is to minimize the error rate without considering the data distribution. And in the worst case, minority samples are all treated as outliers and so ignored. So the learning method will simply build a classifier that classifies all the samples as the majority group. So how should we deal with a case like this? The bad answer is we don't have an overall good solution, and it's always depend on the data. So I will introduce some popular methods, but I will always explain why those are not suitable in this analysis. One easy method at the data level is to balance the two classes by sampling, either oversampling or undersampling. However, simple sampling is not a good choice in this case because the proportion of the minority class is very small, less than 10%. So undersampling the majority class means you will throw out over 80% of the total population. As a result, you lose most of the information. Oversampling either by replicates the existing samples in the minority class or synthesizes new samples using SMOT or other algorithms. They both make variables appear to have lower variance. And also another big problem of doing that is replicating minority class 10 times or higher will definitely cause overfitting. The second kind of approach, which is also very popular, is called anomaly detection. However, anomaly detection simply builds one classification model which consider the majority only. That means it doesn't consider any minority samples. That is something we cannot afford in this project because we will have very limited vision of the data distribution if we only see, if we don't see the 10% of the data. And the last category of method adjust at the algorithm level to make some existing algorithms more sensitive to the rare class. For example, we can adjust the cost for misclassifying any rare event or adjust the decision threshold. But the challenge is how you infer the cost or the threshold unless you have sufficient domain knowledge, which we certainly lack in this project. So what we did in this project is to construct a boosting algorithm that trained several classifiers as weak learners on different portions of the data, and then find the best sets of variables that got selected by most of the weak learners. The last question is how we evaluate the model performance with imbalanced data. Rule number 1, don't use the accuracy or error rate, because classification accuracy is based on a simple count of misclassified samples. So even a naive model that blindly classifies all the minority classes as majority will achieve over 90% of accuracy for this data. And we certainly need to know more than that. For example, we need to know the error rate within each class. So we suggest to use ROC curve to assess the model performance. Let's take a close look at our approach. The first step was to downsample the majority class to match the other one, but instead of just doing it once, we repeated and created a bag of balanced samples by using different random seeds. Each of the balanced data represents just a small portion of the population, but with a bag of it, we have pretty good coverage. The bagging step selects the best subset of variables for each balanced data. And for this project, we chose LARS for doing variable selection. One reason is that LARS is a Lasso-typed method, which reduces the variance of estimates by shrinking the coefficients towards 0. And it generally performs better in the presence of collinearity. In the last step, we count the number of times that a variable was selected in the bagging process and rank the variable importance by frequency. This is a flow diagram you usually see from SAS Enterprise Miner. The top node here is the data source. And we have pre-processed the data to handle missing values, outliers, rare levels, etc. And 20 balanced samples were generated with replacement. Variable selection was conducted at each branch. And variable importance was ranked by the frequency with which the variable was selected in all the 20s. To assess the advantage of this ensemble variable selection, we compared the predictions of random forest, one using features selected by conventional variable selection and the other with features from our approach. This table provides a summary view of this ensemble variable selection. I'm in the left table. From left to right, the first column is the count with which a variable can be selected in the bagging process, and it's ordered in descending order. The second column shows the frequency of variable by each count. The third shows the percentage, and the fourth is the accumulative frequency, which is the running total. If we see the table from bottom up, over 99% of the total 15,000 features were never selected in any of the 20 classification models. And 109 variables were selected only once. So to make a fair comparison with conventional variable selection, we used the top 40 variables, which were selected at least 4 times out of 20. And the number was chosen because if we train our LARS directly on the imbalanced data, LARS will pick the best subset as 42 variables, so which is slightly larger than 40. And we build a random forest on each of the features, the set of features, and compare the model prediction. The table on the right side is the fit statistic table. You can see that the ensemble variable selection outperforms in terms of the ROC index, which is the area under the ROC curve. And the conventional method misclassified 34.5% in validation data, which is almost 5 times higher than the ensemble variable selection method. If you're interested in more details about this project, you can download this white paper. Now let's move on to the second topic, data clustering. Data clustering by its name groups objects into clusters based on their underlying relationships. Say we have n samples x1 to xn, and we want to group them into k segments. Ideally, we would say we want all the samples in the same clusters are more similar to each other, but different to the other clusters. So the core in clustering analysis is to define similarity. With a good measure in terms of high similarity within clusters and low similarity inter-clusters, we can achieve good clustering. The plot here shows a simple 2D toy data, and we can visually distinguish different patterns in this plot. From bottom right, there are 3 nested circles with small, medium, and large radius. And on the upper right, there are 2 spirals with different starting and ending point. The left part has 2 piles of points with different centroids and different distributions. Say if we know the real number of clusters is 7, and we measure the similarity as whether they are from the same shape, we may be able to get clustering as marked on the right side. However, it is not always straightforward how to define similarity, and it could be specific to data. I will introduce several measures that are commonly used, but please keep in mind that they are not always suitable, and sometimes we may rely on experts' opinion rather than some general rules. One measure of similarity for 2 points is the inverse to the distance of the 2. Euclidean distance is the L2 norm of 2 vector, and Manhattan distance is essentially the L1 norm. Kernelized distance is a measure in kernel space through some nonlinear transformation. Here, phi denotes a nonlinear projection function in general. As I mentioned, choosing the proper measure is very important and often requires good understanding of the data. Say in this plot, we have, in the 2 plots, we have 2 different sets, and the color indicates different groups. So my question is, can anyone take a guess which of them should use kernelized distance rather than Manhattan or Euclidean distance? The right side, right? Yes. Because the data on the right side cannot be linearly discriminated, and some nonlinear transformation should do a better job. Defining similarity is often subjective. I already see people laughing at this one. So if we want to talk, like if some people will think, oh, those 2 actually are similar in terms of the hairstyle and the color, but people are laughing or thinking it's kind of ridiculous to talk about similarity between a dog and a person. So whether you think about the species as a variable here will give you just the opposite conclusions. And it's also about how much you value species as a variable over other variables. So different analysts might have completely different criteria and then result in different clustering. There are 2 types of clustering, partitional and hierarchical. One distinction between the 2 is whether the clusters are nested. Partition clustering like K-means or Gaussian mixture models is simply one level division of the data, and the partitions are not overlapping. Given a number K, we find the K centroids so that if all the points are assigned to their closest centroid, the average dissimilarity in the K clusters is minimized. However, as the number K changes, the clusters can change arbitrarily. Hierarchical clustering, either agglomerative or divisive, yields a set of nested clusters that can be organized using tree. Each node, I'm not sure if you can see the dendrogram on the left bottom. So each node, except the leaf node in that dendrogram, is a cluster or collection of subclusters. From bottom up, in this dendrogram, object 1 and 3 are first grouped, also for object 2 and 5. Because those points are closest to each other, as we can see from the contour plot on the right. Then the cluster of 2 and 5 got grouped with object 4 at a higher level, and so forms a nested structure. Keeping merging the closest subclusters or individuals until a single all-inclusive cluster remains. We don't need to preset the number of clusters for hierarchical clustering because we can refine or coarsen the clustering by setting different cutoffs at a different level of granularity. K-mean clustering is a typical partitional clustering, and it begins with, it's of course one of the most popular algorithms in data mining. The goal was to assign each point to one of the K clusters so that on average each point is close to its own centroid. And we first chose K initial centroid randomly. Then each point is assigned to its closest centroid, say mu1 to mu_k. Ck is the set of objects in cluster K. A new centroid got recalculated as the mean of all the points in Ck. Repeat this assignment and update step until no point change their clusters, or equivalently we say the centroid will always remain the same. This is another simple example with only 2 clusters. This can help us to illustrate the operation of K-means. First plot shows the arbitrary centroid at initialization, and K is 2 for this example. In iteration 1, step 1, points are assigned to initial centroids. After the points got assigned, the step 2 is to update the centroid with the new mean. In the next iteration, points are assigned to the new centroid, and so the centroid got updated again and again. We can tell that no matter how far we set the initial centroids, they will always move to some dense part of the data quickly after first several iterations. However, with random initialization, different runs of K-means typically produce different clusters. This is the objective function which measures the quality of clustering. And it is the sum of squared Euclidean distance from each point to its centroid, and we need to minimize it. This objective function always converges in finite number of steps, but is not necessarily guaranteed to achieve the global optimal. Also, the objective function decreases as the number of clusters increase. One way to choose the number K is looking for the elbow shape in this curve over a series of K. However, if there is no such hockey shape in the plot, the selection can be ambiguous. You can also see people using other criteria like gap statistics, CCC, or the ABC criterion that is used in the K-close procedure in SAS-VIA. Hierarchical clustering results in a sequence of nested clusters and can be organized in a tree structure. And it could be bottom-up or top-down. Bottom-up start with all the objects as individual clusters, And at each step, merge the closest pair of clusters or individuals until all the objects in one single all-inclusive cluster. Top-down starts with one cluster, all-inclusive, and then at each stage, split the most heterogeneous cluster until every cluster has only one member. Let's focus on the bottom up because that is more common. And in order to merge the clusters, we need to define a notion of cluster proximity. And here are some popular choices. Single linkage defines proximity as the distance between the closest two points in different clusters. Complete linkage, in contrast, measures the farthest two points in different clusters. And average linkage is the average pairwise distance of all pairs from different clusters. And the distance between centroids, by its name, is easy to understand. It's just the distance between the centroid of two clusters. Ward's method measures the proximity of two clusters in terms of the increase in the objective function as the result of merging two clusters. Here are some pros and cons. One big advantage of K-means is its efficiency. It's fast and can be easily paralleled. But there are also several drawbacks, and people are working on modified K-means to overcome some disadvantages of it. And one of the problems is that K-means is sensitive to the initialization. It often finds local optimal instead of global. So different setups will end up with different clusters. Also, K-mean has no nested structure. If we change K, we can get arbitrary change in results. Hierarchical clustering, in contrast, is relatively time-consuming. But the most fruitful results we can get from hierarchical clustering is actually the tree structure. It's easy to understand and easy to tune, and also it doesn't require any prior information to set the number of clusters. Proc K cluster conducts K-means clustering in SAS-VIF. It's also another powerful and fast procedure in SAS. As the result, Proc K plus generates a data table which contains the cluster membership information for each observation, including the ID of the cluster ID and the distance between the observations and the centroids of the closest cluster. So this concludes the first part of this tutorial. In the next part, my colleague Fonda will talk about some model building techniques in machine learning data mining.